Today, we'd like to present our final project, Needle.compile. PyTorch has a function torch.compile that speeds up code and shortens inference time via optimization passes and then generating optimized kernels. This is especially useful for models that involve many repeated operations that can be fused together. So we implemented this by adding a function, Needle.compile, that you can call on your model after implementing it. On the first run, we dynamically trace the computation graph, compile it down into a custom graph representation, run several optimization passes, generate optimized CUDA kernels, and then execute the graph. We have a global context manager that hooks onto each tensor operation performed and records all necessary metadata. This graph can then be executed in a pre-optimized and post-optimized state, which we compare in our correctness checks.
Common subexpression elimination is an optimization that keeps track of repeated computations to avoid recomputing the same values. To provide intuition, in our example, CSE maps C to D because they're of the same computation. We implement this by traversing nodes in topological order and keeping track whether we have seen it before by identifying based on operation type, references, and other information. If it's been seen, we can map the node to the earlier one. Otherwise, we record it and do necessary bookkeeping. The idea behind that code elimination is to remove computation that is pure, that is, does not affect the program state like division and printing, and does not affect the final output. We do this by marking all impure nodes in the output node as live, and recursively marking all inputs of live nodes as live. Then, we finally remove the nodes not marked as live. Constant folding is the idea of prematurely computing expressions that involve constants. Identities refers to simplifying arithmetic identities such as 0 multiplied by any tensor. These can be done in a straightforward approach by identifying constants and directly simplifying the nodes whenever possible.
Finally, we implemented kernel fusion, which combines multiple kernels into one final optimized kernel, improving cache utilization, memory access, and minimizing kernel overhead. Here you can see this example and the example from our unit tests. So we greedily fuse kernels, represented as a new FuseOp class, and automatically generate optimized fuse kernels for element-wise broadcast and reduce operations. We are also in the process of writing fuse kernels for transpose and NetMull, and also potentially sparse kernels and also kernels for flash attention. Briefly, we show preliminary results. We check correctness against our pre-optimization output, and in our graph, here we see notable final speedups on selected test programs after all of our optimization passes. We also plan on benchmarking later on larger transformer-based models.
Finally,